In this tutorial, we will be discussing cell potentials. In spontaneous oxidation reduction or redox reactions, electrons are transferred as energy is released. We can use the energy to do work if we make the electrons flow through an external device. We call this such a setup as a voltaic cell. A typical cell looks like this. An oxidation occurs at the anode, and the reduction occurs at the cathode. Remember Leo, Ger. Lose electrons, oxidize. Gain electrons, reduced. So knowing that oxidation is losing electrons, the anode is where you lose electrons. The reduction, where you gain electrons, is where the cathode occurs. Once even one electron flows from the anode to the cathode, the charges in each beaker would not be balanced, and the flow of electrons would stop. Therefore, we use a salt bridge, usually a U-shaped tube that contains a salt solution, to keep the charges balanced. Cations move towards the cathode, while the anions move towards the anode. In this cell, then, electrons leave the anode and flow through the wire to the cathode. As the electrons leave the anode, the cations formed dissolve in the solution in the anode compartment. As the electrons reach the cathode, the cations in the cathode are attracted to the now negative cathode. The electrons are taken by the cation, and the neutral metal is deposited on the cathode. Water only spontaneously flows in one way in a waterfall. Likewise, electrons only spontaneously flow one way in a redox reaction, from higher to lower potential energy. The potential difference between the anode and the cathode in a cell is called the electromotive force, EMF. It is also called the cell potential and is designated E cell. Non-spontaneous redox reactions can be made to occur in an electrolytic cell by the addition of electrical energy. Electrons are drawn off the anode, so it must have a place to release electrons, the positive terminal of the battery. Electrons are forced towards an anode, so it must have a source of electrons, and that's the terminal, or the negative terminal, of the battery. These are reactant-favored reactions. Notice if we look on the left-hand side at the voltaic cell, zinc is at the anode and copper is at the cathode. If we look at the electrolytic cell, copper is at the anode and zinc is at the cathode. So they've switched places. This is the reverse reaction for the electrolytic cell. Electric current is used to cause this chemical change. And this is how electrolysis and electroplating are done. Cell potential is measured in volts, 1 joule per coulomb. Reduction potentials for many electrodes have been measured and tabulated. Their values are referenced to a standard hydrogen electrode. By definition, the reduction potential for hydrogen is 0 volts. The cell potential at standard conditions can be found through the equation of the E of the cell, notice the little knot there for standard, is the reduction potential for cathode minus the reduction potential for the anode. Because cell potential is based on the potential energy per unit of charge, it is an intensive property. For the oxidation, or the anode, in a cell, in this cell, the reduction is negative 0.76. For the reduction, the cathode is 0.34. So therefore, as the total cell is the cathode minus the anode. The cathode is 0.34, the anode is negative 0.76, coming out to be 1.10. The strongest oxidizers have the most positive reduction potential, while the strongest reducers have the most negative reduction potentials. The greater the difference between the two, the greater the voltage of the cell. So let's take a look at this one. Determine which of the following materials can be used to oxidize copper without oxidizing silver. Well, here's copper and here's silver. How these are used is whatever above it can oxidize whatever is below it. So for instance, fluorine is above both of them, so it can reduce both. I minus is on this side, so it would have to be the reverse reaction. So that would work for silver, but not with copper. I2 is right here. It can oxidize copper without oxidizing silver. And then chromium would not oxidize either. A spontaneous reaction will take place when a reduction half reaction is paired with an oxidation half reaction lower on the table. You will look at the reactant that is being reduced and see if it's above the other reactant. So if we compare copper and zinc, here's copper and here's zinc. If we look at the reaction, in this one, we're looking at the one that's being reduced. So we're looking for the one that's gaining electrons reduction. So we're looking for the one that's gaining electrons. Zinc here is losing electrons. So that's being oxidized. Copper is gaining it here. So, since copper is gaining electrons and it's above the zinc, that means it will be spontaneous. If we reverse this, it becomes non-spontaneous. Another way to look at this is the fact that in this one, it's 0.34. Notice that it starts off with solid zinc, which is on the right hand side. So that means this one is going to be the minus. Alright, determine whether each of the following is spontaneous as written or in the reverse reaction. Alright, so F2 is here, and then I minus is down here. F2 is above iodine, so therefore it will be spontaneous. Magnesium is here and silver is here. Look at the one that's being reduced. Magnesium is losing electrons. Silver is gaining electrons. So therefore, the one that's gaining electrons has to be higher in the chart. Silver is higher than magnesium. So that's spontaneous. Copper here is gaining electrons, while iodine is losing electrons. So, by that, copper is here. I want to look at the one that's gaining electrons. Iodine is above it. Because of that, it's not spontaneous. Here, copper is going from a +2 to a 0. It's the one gaining electrons. Chromium is going from a +2 to a +3, which is losing electrons. So we want to make sure that copper is above chromium, and it is. So it's spontaneous. Balanced half reactions can be added together to get an overall balanced equation. For instance, zinc yields zinc 2 plus and 2 electrons, while copper plus 2 electrons is equal to copper solid. We can combine them and cancel out the 2 electrons. From each half cell reaction, the energy of the cell, the potential charge, can be calculated, the cell potential. If you know the E cell values for each of them, we can just add them together. When adding the E naught values for the half cells, do not multiply the half cells even if you multiply the half reactions to balance the equation. Alright, so let's take a look at this one. Let's figure out what's being oxidized and what's being reduced. First of all, that I minus is going to the I0. This one is being oxidized. It's losing electrons. The IO3 is going to the water. This is the reduction half. Notice here is the equation for that reaction. That's going to be our cathode. Even though the balanced redox has a different stoichiometry than the E cell, it is not multiplied. E cell is an intensive property of matter. Alright, so the cathode minus the anode. So the cathode, which is right here, 1.20, minus the anode, 0.54, you get positive 0.66. So therefore, it is spontaneous. And that's how you do cell potentials.